right, so to get a derivative at any point, our f prime of x, I'm just going to review that formula for you. You did it on your quiz. It was limit as h goes to 0, f of x plus h minus f of x all over h. And so that gives you f prime. And then you can plug in any number you want. You could find f prime of 0, f prime of 2, f prime of 17, you know, whatever you needed. But say you only needed the derivative at one specific point. You have a little bit of a shortcut method, like say, this says c, but c could be any number. Let's say you just needed f prime of 3 and that was it, and you wanted to just jump straight to the answer, then this would be the formula you would use. So limit as x goes to c, so again, whatever that c number is, like limit as x goes to 3 or whatever it is. It would be the function minus f of c over x minus c. And if that looks like the slope formula to you, subtracting the y values and subtracting the x values, that's because it is. A derivative is slope. And that's really what this formula is too. This is just like the general formula, and then this is at a specific point. So for number 1, it says find f prime of 2 for this function. So if you wanted to do it the longer way, you would have to get f prime and then plug in 2. But if we use this formula, we can just jump straight to the answer. So if we want to find f prime of 2, it will be limit as x goes to 2, and then it's the function. So I'm just going to copy the function down, minus, now this says f of c, but for the problem we're doing, that would be f of 2. So I'm going to plug 2 in for x, and whatever I get, that's what's going to go right here. So 2 squared is 4, times 3 will be 12, and then plus 2 will be 14. And then it's over x minus c, so this would be x minus 2. Now, spoiler alert, if you plug in 2 for x, you're going to get 0 over 0. It's not going to work out. We're going to have to factor this and get something to cancel. So splitting the numerator is going to give us 3x and 1x. 14 is going to split 7 and 2. And to get a positive 1x in the middle, we would need positive 7 and then minus 6 for the outside. And one of those factors was going to have to be x minus 2 so that we could get these to cancel. And once we do, then we can plug in 2 and get our answer. Now, it's not f prime of x that we're finding, it's specifically f prime of 2, just the derivative at that one place. So if I plug in 2, 3 times 2 is 6, plus 7 is 13, and that's our answer. So this formula is a little quicker when you just want the derivative at one number. If you wanted to get the derivative at several different values, you would want to find f prime and then use that to plug into. So it just depends on what you want to do. So for number 2, here's our piecewise function. Is the function continuous at 3? So what we need to check is, do these two pieces meet and match up? So we're going to plug 3 into both parts of the function and see if they equal the same thing. Oh, sorry, I saw a question in the chat. The question is, where did the x minus 2 come from? In the denominator for the formula that we're using, it says x minus c. For this problem, our c value was 2, so it was x minus 2 in the denominator. It'll just be x minus whatever number it was that you were trying to find the derivative at. So it came from this part of the formula. Okay, cool. Number 2, so here's our piecewise function. If the function is continuous, then the two parts will meet up. So I'm going to plug in 3 for both of them and just kind of see what we get. So plugging in 3 for the numerator, that'll be 3 squared minus 2, which will give me 7. And if I plug in 3 to the second part, 2 times 3 plus 1 is also going to give me 7. So yes, the function is continuous. both pieces of it met up at the point 3, 7. But is the function differentiable? Well, not necessarily. If they meet at a sharp edge, then it's not going to work. So what we need to do is test the derivatives from the left and from the right. So we're going to use this formula that we just went over here. And we're going to approach 3 from the left and from the right. So I'm going to do limit x approaches 3 from the left. And I'm going to use the first piece of the function because that's where numbers smaller than 3 are. So it will be the function, so x squared minus 2. Here, let me move this back down again. It's the function, and then minus whatever you get when you plug in the value. So minus whatever we get when we plug in 3. And we already did that. When we plugged in 3, we got 7. So that'll be 7. And then it's over x minus whatever value it was you were approaching, which in this case is 3. I know it's 3 from the left, but still just 3. So in the numerator, if I combine those like terms, that's going to be x squared minus 9. And then that is going to split x plus 3, x minus 3. And so the x minus 3s are going to cancel. And if I plug in 3 for x, I'm going to get 3 plus 3, which is 6. So that means my slope, again, remember derivative means slope. My slope from the left side is 6. So now I need to check the derivative from the right side. So I'm going to repeat this process from the right side and see if I also get 6. So limit x goes to 3 from the right. And that just means I'm going to use the second piece of the function where I've got numbers bigger than 3. So that will be 2x plus 1. And then it is minus whatever you get when you plug in 3. And again, we already did that. When we plugged in 3, we got 7. So that will just be 7. And then over x minus 3. Once again, I'm going to need to combine some like terms and factor the numerator. So I've got a couple of steps of work here. So if I combine those like terms, that will give me 2x minus 6. And then from the numerator, I can factor out a 2. So that will leave me with x minus 3. And so those cancel, and all I'm left with is a 2. So I can't even plug in 3 here at the end because all the variables canceled out. So just 2. And so what that means is my slope from the right side is 2, which should actually make sense because that right side of the function was linear, 2x plus 1, and the slope was 2. So that should make sense that that slope was 2. But what's happening here is our slope from the left and our slope from the right are not matching up. So this function is not differentiable. So as continuous, the two pieces met up, but not differentiable. And this is just, if you're a visual learner, this is what it would look like. I always need a picture. The first piece of this function was a parabola, x squared minus 2. So it was doing something like this. And then where they met up, it turned linear and it did something like that. So that's just a brief visual of what that would look like. And so you end up with that sharp edge there. The two slopes were not equal to each other. So one of them was 6 and one of them was 2. So not differentiable. So to kind of pull this all together, a function is differentiable if you have no discontinuities. I know that's a big word, but no discontinuities means the function has to be continuous. So ways that this can be a problem, your discontinuities, are if you have an asymptote, or a hole in the graph, or a hole and then the point is somewhere else, or if you have a jump. Those are all your discontinuities. And so if your function's discontinuous, then it's also not going to be differentiable. You can't get derivatives at places where there's not even a point, or places where you have a jump like that. You're not going to be able to get a derivative there. The slopes from each side aren't going to meet up. So no discontinuities. And we talked about this one last time, no sharp edges. And that means a corner or a cusp. So a corner would be something like the absolute value graph. A cusp looks something like this, like the way that I would draw a bird flying. But I just call them sharp edges, and then that covers all manner of sins. And just any place that there's a sharp edge, your slopes each side aren't going to match up, so you can't get a derivative there. Those two people remember pretty well. It's this third one people forget about, so maybe, like, I don't know, put a star next to this one. No vertical tangent lines. No vertical tangent lines. And that's because, well, let me ask you guys this question. What's the slope of a vertical line? What would be your slope of a vertical line? Yeah, good, undefined. Yeah, none, there isn't one. So it's sort of like by definition, you can't get a derivative there. It would look something like this. You'd end up with a vertical tangent line there in the middle. And a derivative means slope, and the slope of a vertical line is undefined. Just by definition, there isn't one. So, so those are your rules for being differentiable. You can't have a discontinuity, you can't have a sharp edge, and you can't have a vertical tangent line. So I want to real quick, before we do some of these examples, just put out a couple statements here. If a function is continuous, so if a function is continuous, it is not necessarily differentiable. So if a function is continuous, it's not necessarily differentiable. And that's like the example we just did on the other side, where we had the parabola and the line meet up. The function was continuous because the two pieces connected, but it wasn't differentiable. So if a function is continuous, it's not necessarily differentiable. But if a function is differentiable, it is continuous. So if a function is differentiable, then it is continuous. It would have to be. If you can get a derivative at a point, your function has to be continuous. All right, let me read in the chat here. When you say the other problem, do you mean the one that we did with the parabola and the line that met up, this one right here? Yeah, it's just a sharp edge there. So where the parabola and the line meet, it's not like a real smooth curve. The slope from this side, like if I was drawing in a tangent line here, that slope would be 6, whereas this slope is 2. So you end up with a sharp edge there. It's really difficult to get two graphs to meet up and have like a nice smooth curve there, but there are some that do, so you always have to check. So yeah, it was a sharp edge. But thanks for bringing that up again, because my point is this function is continuous. You can trace it without lifting your pencil off the paper, but it's not differentiable. But if your function's differentiable, then it is continuous. And that comes up on the AP exam, because they'll tell you blah, blah, blah function is differentiable, and then you'll have to go, okay, so it's also continuous. So that does come up. So for these, we're going to state, or we're going to discuss the continuity and differentiability of the functions. So what do you guys think for number 2, absolute value graph, continuity? Is this function continuous? Yes. I don't know. Are we being shy here? Continuous. Can I trace it without lifting my pencil off the paper? Hearing yeses from 2 of you. No one else wants to say anything. Okay. So yes, we are continuous for the entire number line. Continuous on all reals. All right. So is this function differentiable everywhere? Good, that's where we have a problem, okay? So we are not differentiable. Can I abbreviate differentiable? Is that okay with everybody? If I call that diff, write out differentiable. It's spelled out right there. I'm never gonna grade you on spelling, okay? We can abbreviate. We're not differentiable at x equals 0 due to a sharp edge. For these ones here, all I did was give us a graph, so we can just say due to sharp edge or due to whatever the problem is. But on the AP exam, oftentimes they'll give you a function and you'll have to go through these limits like I did, limits from the left and from the right. So just remember, this is another way you can get through this problem. Okay, I'm showing you both, but remember the limits. All right, number 3, we have an asymptote at 2. So is this function continuous? Good, no. We are discontinuous at x equals 2 because f of 2 does not exist. We don't have a point at 2. Remember your rules for continuity. There's a point, there's a limit, and they agree with each other. They equal each other. Well, we don't even have a point at 2. There is no point at all there. Sounds like I'm saying the graph is pointless, but just at 2. So if the graph has a discontinuity, then we're also going to be not differentiable at 2. So not differentiable at x equals 2 for the exact same reason, because we have a discontinuity. If we're missing that point entirely, we can't get a derivative there. All right, so for number 4, is this function continuous? Yes, good. We can trace it without lifting our pencil off the paper. So we are continuous on the entire number line. But we are not differentiable. We have a cusp there. So not differentiable at x equals -3 due to sharp edge. And again, I don't have an equation for this. So I can't like do the limit from the left and from the right. But again, on the AP exam, sometimes they'll give you an actual equation and you would have to do the limit from the left and the limit from the right. But if I draw in tangent lines, like, do you see that they don't, like the slopes would not be the same? If I draw in tangent lines at that point, it's not gonna work. All right, and then the last one's a parabola. So that is continuous everywhere. And is it also differentiable? Yeah, good. So we're differentiable on all reals as well. There are no sharp edges, there's no vertical tangent lines, there are no discontinuities. And every polynomial is going to be continuous and differentiable. A quadratic is a type of polynomial, like x squared, x to the third, x to the fourth. In fact, let's just go ahead and put that in our notes. All polynomials are continuous and differentiable. So if you're told such and such is a polynomial, then you know it's continuous and differentiable.